2024 TA candidates. I'm making this video for the TA workshop. I'll post it on River so you all can see it. I'm gonna talk about how we will go deep into a one-way ANOVA and try to understand how it works. My name is Walter Maru. I'm a senior teaching assistant of the PPCR course since 2015. I'm also a plastic surgeon. And without any more, we'll get into analysis of variance, ANOVA. To understand analysis of variance, we have to understand two concepts. The first one is the statistical ratio, and the second one is variance. Okay? So, the concept of statistical significance for comparing means is based on the relationship between two sample characteristics, the mean divided by the variance. So, when we say mean, what we actually mean is the difference in means or the difference between two groups. This will determine the effect size. And when we talk about variance, we will talk about the variability of scores within a group. And this is because not all participants respond the same. This is called the error variance. So we see here in graph B, for example, when we have two groups, okay, one control group and one experimental group, and we see for each group a distribution of scores. And we see a distribution of scores because, as I said before, not all participants respond the same in each group. Some will respond a little bit better than the mean, some will respond a little bit less than the mean, and that's why you get a distribution, okay? So when you have these two distributions of these two groups, one the control group and one the experimental group, you can have some interesting things. For example, if the means of the two groups are farther apart, that means that the difference between means will be higher. So it will be easier for you to find statistical significant differences. But not only that, even if the two means stay the same, but the variability within groups increases, then it will be much difficult for you to find differences or statistical significant differences. But if the variability decreases, it will be much easier to find statistical significant difference. So, as I said before, that not all participants respond the same within each group, any given score from a participant will be a composite of the effect size, the real effect size, plus the error variance of the variability or the variability of the participant within the group. Here we can see it a little bit more clearly. Here you have a control group, here you also have your experimental group, and here you have your distributions of scores for each of the groups. Okay? So what we can see here is this. When the difference between means increases, it's easier to see statistically significant differences within the groups or just differences within the groups. And also, if the means stay the same, but the variability within groups decreases, it's also easier to find differences between the groups. So that's what the statistical ratio is. Okay, the statistical ratio is nothing else than the difference between means divided by the variability within groups, meaning that if the difference between means increases, you'll have a bigger number in the numerator and your statistical ratio will be more than 1. If the variability within groups decreases, that means that you have a smaller number on the denominator, which will also make your statistical ratio a bigger number. So when you have a big statistical ratio, it's easier to find statistically significant differences. Okay, so here we can see also that the statistical ratio is the treatment effect plus error, which is the difference between means, divided by the error, which is the variability within groups. What I want to explain here is that if the treatment effect is pretty small, the statistical ratio will be close to 1 because it will be like error divided by error, okay? But if the treatment effect is big or big enough, you'll see a bigger number in the numerator, then your statistical ratio will be a bigger number, which means that it will be easier to find differences between groups. So, as the statistical ratio increases, the possibility of finding statistical significance is much higher. Now we'll get into a little bit of the concept of variance. Variance is a measure of variability. The easiest way to measure variability around the mean is by using deviation scores. Deviation scores is nothing else than a score of a participant minus the mean. Okay, it's the difference between the score of the participant and the mean of the group. So the bigger your deviation score, the bigger the variability around the mean. Okay, remember that variance is a measure of dispersion, so it will measure variability. So as I was telling you, the bigger your deviation score, the bigger the variability around the mean. You can even get a mean deviation, score if you do this. So you divided your deviation score by your sample size. But is that a good idea? No. Why is not a good idea? Because if you get a mean deviation scores, you'll probably get 0. And this is because means are central tendency measures. So it's a central balance point for distributions, meaning that scores will be equally dispersed above and below the central point. Okay, so you will have negative numbers and positive numbers. And when you take the difference of all those numbers, it will add up to 0, which is of not help at all for us. So how we go around this problem? Statisticians are intelligent, so they square the deviation scores to get rid of the minus signs. This is the magic, okay? And this is called the sum of squares, a very important term we need to understand. So, still we have one problem though. The bigger the sample size, the bigger the sums of square will be, because we will just be adding numbers, but not really meaning that our variability increases. It's just because we'll have more numbers to add in the summation. So statisticians decided that to fix this problem, they could divide the sum of squares by the sample size, making a mean of variability or dispersion. And this division of the sum of squares by the sample size is what's called the mean squares, or which is also called the variance. And this is a formula: the sum of squares divided by the sample size. So here we have an example of 8 scores, okay, which have a mean of 17.25. Here is your dispersion score, like 9 minus 17.25 is minus 8.25. And the same with the second score, the third score, and you add them all up. So here you see in practice what I was telling you in theory. If you add up all your dispersion scores, you'll get 0. Why? Because as I told you, the mean is a measure of central tendency. So what statisticians did, the magic, is you square the sum of squares, so you get rid of the minus sign. So now when you square this sum of this deviation score, you'll get your sum of squares. And your sum of squares will be 273.48. Okay? Now what you do? You divide your sum of squares by your sample size, which will be n minus 1 because it's a sample. So you use the degrees of freedom, and degrees of freedom for this will be n minus 1. So it will be 273.48 divided by 7, so your variance will be 39.07, sorry. But you remember that your sum of squares is the square of your deviation scores? Okay, so now to unsquare it, you just take the square root of your variance. And the square root of your variance will be your standard deviation, which will be 6.25. And 6.25 is your mean variability score around the mean. Understand? Pretty easy, right? Now, I'll talk to you a little bit of the concept of ANOVA. ANOVA is an acronym for analysis of variance, and it can be used when the independent variable has more than 2 levels. Then you use a one-way ANOVA, meaning that your experiment has more than 2 groups, 3, 4, 5, 6 groups. Okay. You can also use it when there is more than 1 independent variable. In that case, you'll use a two-way ANOVA. You can also use it when repeated factors are used to evaluate the performance of each subject. That's called a repeated measures ANOVA. You can also use it when the independent variable has more than 2 levels and that is non-parametric. Then you'll use a Kruskal-Wallis ANOVA. And another example is a repeated fact when repeated factors are used to evaluate the performance of each subject and data is non-parametric. In that case, you'll use a Friedman ANOVA. As you see, there are lots of types of different analysis of variance, but today we'll just focus in the simplest one, which is a one-way ANOVA, and we'll see how it works. So, as I told you, for the concept of ANOVA, you have to mix two concepts that we just studied, which is the statistical ratio, which is the difference between means divided by the variability within groups, and the variance, which is the sum of squares divided by the sample size. What are the statistical hypotheses for a one-way multi-level trial using ANOVA? The null hypothesis is that the mean of the group 1 will be the same as the mean of the group 2, the same as the mean of the group 3, and the same with the mean of all the groups. There will be no difference between means within the groups, between the groups, sorry. And the alternative hypothesis is that at least two means will differ. What are the assumptions of using ANOVA? ANOVA is one-way ANOVA is a parametric test, so you'll have to search for normality and a normal distribution of all your groups. You have to look for homogeneity of variance within all your groups. Your samples must be independent and your groups must be randomized. Now, how this works? For example, this is a simple example when researchers uh, try to use four different mechanisms in order to increase elbow range of motion after elbow trauma. The first group, they put ice to the elbow. The second group, they use NSAIDs. For the third group, they splint the elbow. And the fourth group is only put the elbow to rest for some days. Okay? So they want to see how these techniques affect the range of motion and if one or more of these techniques are better than the other to increase the range of motion of the elbow in patients that have had a trauma in the elbow. Okay, so you have four groups here: ice, NSAID, splint, and rest. The first thing you do in an ANOVA is you pool all your groups to create one big group, and you take the grand mean of that mean group, of that big group. This will be the grand mean, okay? Remember, these four groups are pooled into one big group, and you take the grand mean of that big group, okay? That's the first thing you do in an ANOVA. Doing this will give you the total sum of squares, okay? Perfect. And what's the total sum of squares? Total sum of squares is nothing more than the deviation scores of this big group, which mixes the four small groups you had before, squared. And this is the formula for the total sum of squares. Now you have to partition your sum of squares. The total sum of squares, or the total variance, will be divided into two variances. Between groups variance, which will be the difference between means, and your within groups variance, which will be the between subject variance or your error variance, or the variability of scores within each group. Okay, so it's a super easy formula. The total sum of squares equals the sum of squares of your between groups plus your sum of squares of your within groups. Okay, so why we did this pooling and get this grand mean of these four groups? It's super easy, because when we pool these four groups into one big group and take the grand mean, which is this red line here on the graph, then we can compare the other means to this grand mean. So we'll just take the other means as independent scores and we'll compare those scores to this grand mean and see if the difference between each mean and the grand mean is big enough to have a statistically significant difference for one or more groups. So, and now you will take the sum of squares of the between groups, which will be the treatment effect. Okay, what I mean getting the sum of squares of the treatment effect or the sum of squares of the between groups is nothing else but having the sum of squares of each of the means compared to the grand mean. Okay, so this is the formula of the sum of squares between groups. Okay, it's super easy. Now, we have to take the sum of squares of the within groups, which is the sum of squares of the error variance or the variability of the scores within each group. So to do that, we just get our dispersion scores for each group, okay? We square that, okay? And we add them at the end for the 4 groups. So here we are finding the sum of square of each group mean and adding them up. And that will be our within group sum of squares, which will be our error variance. So until now, we have been messing around with the top part of the variance equation, just talking about the sum of squares, you know? But remember, what was the problem with that? That the bigger the sample size, the bigger the sum of squares will be, because we will just be adding numbers, not really meaning that the variability increases. So to correct this, we will divide our sum of squares by our sample size. And as this is a sample, we'll use degrees of freedom and not the actual sample size. So here is what I say. So statisticians decided that to fix this problem, they could divide the sum of squares by the sample size, making the mean of variability or the mean of dispersion scores. So this is called the mean square or variance. Remember, we see this some slides before. So we will do this to your between groups sum of squares and to your within groups sum of squares. And how you do this? Okay, to get our between groups mean square, we will divide the between groups sum of squares divided by the degrees of freedoms of our between groups. And to get our within groups mean square, we will divide our within groups sum of squares divided by the degrees of freedoms or the within groups. Here are how you get those degrees of freedoms. Total degrees of freedoms is sample size n minus 1. The between group degrees of freedom is only the number of groups minus 1. Remember, because we are treating each group as an individual score, so it will be like, if we had 4 groups, it will be 4 minus 1. Our degrees of freedom of between groups will be 3. And the degrees of freedoms of our within groups will be the total sample size minus our number of groups. Okay? Super easy. Then we'll talk a little bit about the F statistic. Why it's called the F statistic? Because it was invented by Sir Ronald Fisher. Clever, right? Well, the F statistic is nothing more than the statistical ratio we've been talking all the lecture applied to the variance. Remember, statistical ratio is the difference between means divided by the variability within groups. So in case of analysis of variance or ANOVA, the statistical ratio will be called the F ratio, which means, or which is, the mean square of between groups, which is the treatment effect, divided by the mean square of the within groups, which is the error variance. Now, when the null hypothesis is true and no treatment effect exists, the total variance in the sample size is due to error, and the mean squares of the within groups is equal to or larger than the mean squares of the between groups, yielding an F ratio of approximately 1. That's when there's no treatment effect, or when the treatment effect is super, super small. But when the null is false and treatment effect is significant, the between group variance is large, remember, yielding an F ratio greater than 1. So the larger the F ratio, the greater the difference between the group means relative to the variability within the groups. So if your F ratio is bigger, you have more probability of finding statistically significant results. What does statistically significant results in ANOVA means? It doesn't mean that all groups are different from each other. It just means that at least one group, if different from, is statistically significant. It has a statistically significant difference from the others. Okay? So to see which of my groups is the different one, we'll have to do a multiple comparison test, mainly a Bonferroni test, but that we'll talk in another moment. So the F ratio. As every statistical ratio, it has a distribution. In this case, it's called the F distribution. Pretty creative, huh? F distribution, F ratio, Sir Ronald Fisher. Okay, well, this is the distribution. What I want you to see, guys, is that this distribution starts ends at 0. It has no negative numbers. It's not like the t distribution, which has negative and positive numbers. And why does it start at 0? Because remember, we have squared our deviation score. So when we squared the numbers, we take out negative numbers. There are no negative numbers, no possibility of having negative numbers. So we'll only have one tail in a F test or in a ANOVA test. We don't have to differentiate between tails, two tails, one tail, as in a t test. The critical values of F. Well, like t, the calculated F ratio is compared to a critical value to determine its significance. Because mean squares are based on square values, the F ratio cannot be a negative number, as I told you before, and therefore we do not distinguish tails for an F test. So, to reject the null and achieve statistical significance, the calculated value must be greater than or equal to the critical value. A significant F ratio does not indicate that each group is different from all other groups. Actually, it only tells us that there is a significant difference between at least two of the means, the largest versus the smaller. So, this is how you get your critical value. You use your degrees of freedom. Degrees of freedom from your between groups and the degrees of freedom from your within groups. Okay? For example, if you have a degrees of freedom from your between groups of 3, and if you have a degrees of freedom from your within groups of 20, your critical value will be 3.10. So if your statistical ratio or your F ratio is equal or greater to 3.10, then you'll have statistically significant results and a p-value less than 0.05. So this is a summary table. Here you see. Here you have your between groups. Here you have your within groups or error variance and the total. When you get your dispersion scores squared of your between groups, you get your sum of squares of your between groups. When you have your dispersion score squared of your within groups, you'll have your sum of squares of your within groups. And as we see earlier, and as we saw earlier, the total sum of squares is nothing but the between group sum of squares plus the within group sum of squares. Okay? Here you have your degrees of freedom for your between groups, which is the number of groups minus 1. This is your degrees of freedom for your within groups, which is the sample size minus the number of groups. And this is the total degrees of freedom, which is the sample size minus 1. Okay? So you have your sum of squares and your degrees of freedom. Now you'll get your mean squares. To get your mean squares of your between groups, you just divide your sum of squares of your between groups by your degrees of freedoms of your between groups. And to have your mean squares of your within groups, you just divide the sum of squares of your within groups divided by the degrees of freedom of your within groups. And when you do this ratio, get the F ratio, the F ratio will only be your mean squares of your between groups divided by your mean squares of your within groups. Remember, your F ratio must be equal or larger to the critical value that you took on that you get on the table, and if the F statistic is equal or bigger than your critical value, then you have a p less than 0.05 or a significant result, meaning that at least two of the means are different from each other. Or you can summarize the last 15 slides with one stata command, which is much easier, right? Which is the Oneway ANOVA stata command, which is one way, dependent variable, independent variable. You put that and you'll get your a stata ANOVA table, which will tell you like summary between groups, within groups, sum of squares, degrees of freedom, mean squares. When you divide your mean square of your between groups by the mean squares of your within groups, you'll get your F statistic, and your F statistic is compared with the critical value. Stata does this automatically, and here you'll have your p-value, which is significant, obviously. Okay, guys, that was all I had to talk to you about. Hope you like it, and any questions, please you can put it in your comments, and I will answer them shortly. Thank you so much. Bye.